Okay, Assalamualaikum warahmatullahi wabarakatuh. So this is the lesson for DC drive using chopper, or we know as a DC to DC converter. So this is actually the typical or conventional block diagram on how we actually control the speed of the DC motor. So as we already know that the speed of the DC motor is controlled by the voltage DC input of this DC motor, and in order to get a variable DC voltage input here from an AC source, so this is actually the system where, as you can see, the AC motor is coupled with the DC generator, and this DC generator will produce the variable DC voltage, okay, by controlling the circuit IF here by having the variable resistance here. Okay, so this system, as you already see from here, is actually very bulky because it has, you can see, involved an AC motor, DC generator, and so on to produce the variable speed. So it's very bulky and inefficient because we have several steps of power conversion here, and inflexible. Okay, so this is the modern electrical DC motor drive. So we have this source, okay, we have this DC source here, which is a fixed DC source. So we are using power electronics, and the power electronic will produce the voltage and current for the motor, and then this voltage and current will be feedback to the control unit, and then so this control unit will produce right now the input for this duty converter. So actually for this one is actually the input is actually what we call a duty cycle. Okay, so as can be seen from this slide, so actually by using this power electronics converter, so actually the system will become more small in size, and then efficient, meaning that losses is reduced because we are using power electronics as a switch, and then more flexible in terms of having in actually to adjust the system. Okay, so this is actually the applications of the adjustable DC motor drive. So as we can see here, this one is actually compressor, okay, compressor in the aircon system. So actually we control the speed of the motor by controlling the power electronics converter switching. So I would like to mention again for the quadrant of operations. So actually we have 4 quadrants, and actually your DC motor is capable to actually function in 4 quadrants, which is forward motoring, forward braking, reverse motoring, and also reverse braking. And this is actually depending on the torque and also the speed. Okay, so torque is proportional with the current, and the speed is actually proportional with the voltage input. Okay, but the limitation is on the quadrant operation is due to the converter itself. So there are converters that only can be used to operate in the single quadrant, and there are also a circuit DC-DC converter that can only operate 4 quadrant, and there's also a circuit that can actually conduct in all 4 quadrants. So there are 3 types of drive systems, and it depends on your application. Some of the application requires only single quadrant. For example, on this your DC drive only requires forward motoring, quadrant operation on, so you don't need to use the 4 quadrant circuit. Okay, so this is actually what we just maybe we revise again. So this is actually the quadrant forward motoring. Okay, and then this is the second quadrant for braking, and then this is the third quadrant reverse motoring, and the fourth quadrant reverse braking. Okay, so this is the all 4 quadrant operation of the DC motor. Okay, And I would like to mention again, not all converters can operate in all 4 quadrants. Okay, so that is the limitations. So, and then this is actually the relationship between torque, speed, and also the power produced. So for the drive to able to operate in 4 quadrants, the power-to-weight converter must be capable of supplying the voltage and current in all quadrants of voltage and current. So meaning that, as you can see here, we have 4 quadrants. So it depends. Okay, so as you can see, this is I. So I must be positive, P also positive. This one current must be negative. This one voltage is positive. This one current is negative, voltage is negative. This one current is positive and voltage is negative. Okay, so meaning that in order to power electronic converter to operate in all 4 quadrants, so this power converter need to actually supply voltage and also current for both positive and negative, positive and negative. So, okay. And I would like to also maybe a brief revision. So this is actually the equations. Okay, so this is your armature circuit equation. So this is your field circuit equation. So in steady state, this is 0. Okay, steady state. So this term will become 0. This one also will become 0 in steady state. So actually for this equation in steady state, we can reduce this as a VT RAIA plus EA only. And for this field circuit, we can reduce this as a RF IF. Okay, for steady state operation. And you also need to know this equation, the torque equation. This torque is actually proportional with the armature current. And we have also need to know this equation. Okay, so there are actually 4 equations that need to be remembered in order to solve the motor drive problems. Okay, and also one more thing is actually this what we call EA is actually a back EMF. So this is actually a voltage that produced due to the rotation of the DC motor itself. And sometimes most of the time, as you can see here, we have KT, KE, and so on. So most of the time, KT is actually equal to KE. Okay. So as you can see, we have 3 types of DC chopper. So we have one single quadrants. So and then we have 2 quadrants of DC chopper, and we have also 4 quadrant DC chopper. Okay, so I would like to. So this is actually the DC chopper that can only operate in quadrant number 1, which is only forward motoring. Okay, so for motoring, based on the speed and torque, so the speed is positive, torque is also positive, so meaning that the voltage AVA, IA is also must be positive. Okay, so as you can see here, okay, this is the operations inside the circuit when for the single quadrant. Okay, so this is actually based on this circuit. So actually the 2 parameters that very important is actually the operation of the T1 and also the operation of the diode. Okay, so as you can see here, when T1 is on, so actually the diode will actually reverse bias, and the voltage, the current will flow and charging the inductor of the DC motor. And as you can see here, the current right now is actually charging. Okay, and then as we already know that for the inductor, so in 1 cycle operation, so this is actually 1 cycle operation. Okay, 1 period of operation. So the current of the inductor must be go back to its starting value. For example, if the current is starting at this one, so actually for at the end of the cycle, the current must go back to its starting value. So as you can see here, so that's why you can see we have right now T1 is on, okay, so the inductor will charge, okay, and then we need to discharge the inductor. So in order to discharge the energy that currently has been charged in the inductor, we need to discharge, okay, discharge the energy. So in order to do that, T off must be turned off, and this T off must be turned off, and T1 will be forward biased. So as you can see here, the current, the energy will be discharged freewheeling through inside this circuit. Okay, so that's why you can see that the current is starting to discharge and go back to its minimum value. So this is actually the basic principle of controlling the DC motor. So actually, we need to make sure that the current of the inductor to go back to its initial value at the end of the cycle. And this is a single quadrant, so meaning that the current is positive and the voltage must be positive. So as you can see here, the current of the inductor the current of the armature circuit is always positive for both when the switch is on and when the switch T1 is off. Okay, so the current is always positive. Current direction is always from the source to the load, which is the DC motor. So the current is positive, the voltage is also positive. So as you can see here, this is the current waveform. So we have minimum, maximum, minimum, maximum cyclic waveform. So due to this cyclic waveform, you always will have IA average. Okay, so IA average is actually a positive, and this is actually the waveform of the V out across here, which is not a V out, which is we can actually also define as a V armature. Okay, so based on this, our V armature should be always positive. Okay, so what is the value of the VA? So the value of the VA, as you can see, is actually equal to dVdC. So it's actually a buck converter. So V armature is actually D multiplied with VDC. And what about the value of IA? So IA is actually based on the KVL equations of the DC motor. So it's actually a VA minus EA over RA. So where the VA is actually a dVdC minus the back EMF over RA. Okay. So this is also two equations. So we can actually got the VA equations and also IA equations. So this is actually circuit for this two quadrants. So this circuit is actually able to actually conduct in two quadrants, which is forward motoring and also forward braking. So meaning that this circuit must capable of producing positive VA, positive IA, and positive VA and negative IA. Okay. Okay. So for the quadrant number one, so how this circuit operate in quadrant number one is actually equal to this previous circuit. Okay, actually equal to the previous circuit. So actually for this circuit, okay, for the quadrant number one, okay, T1 will actually on first. T1 will on. Okay, so meaning that you will have current. Okay, current actually charging, as you can see here right now, the current is charging. Okay, And then the current also we need to discharge to complete one cycle. So T1 will off and D1 will turn on. Okay, and then so this current energy inside this inductor will actually discharge. Okay, so the direction of the current still in the positive direction. Okay, so as you can see, this is during the charging and during the discharge. So both current are positive and the voltage across the armature is also positive. So this is for the quadrant number 1. And the same circuit can be operated also in second quadrant. So how this circuit can be operated in the second quadrant? So for the second quadrant, you should know that VA is positive and IA is negative. So how to make IA is negative is actually T1 must on first. Okay, T1 must on first. So meaning that this motor, which is back EMF, will act as generator. So it will charging this inductor. So as you can see, the current here is actually charging, okay, towards positive. Okay, and then you will see that actually this current direction is from load to the source. Okay, from load to the source. So negative IA. So that's why we have here. But right now it is charging the inductor. So we can see that the current will actually increase. Okay. And to discharge this inductor, okay, so T2, this transistor must be turned off and D2 will actually forward bias. And as you can see here right now, the current will actually discharge through the source. Okay, so as we can see here, the current will be discharged, okay, from the motor, go back to the source. So IA is negative for both condition, T2 on and D2 on. So that is how we actually can make VA is still positive, but IA is negative. Is actually by controlling the switch of T2. Okay, so same. So still, the VA is actually a DVDC, and your IA is still the same. Okay, this is IA. So this is your VA. And this is actually a circuit for DC-DC converter that capable to operate in all 4 quadrants. Okay, so the explanation is actually similar to the explanation that for the first quadrant and second quadrant. Okay, so I leave it to you all to actually see through these slides, okay, on how it is operated. So actually this motor is actually, I don't want you to confuse. So actually this motor is comprised of this circuit, RALA, and also back EMF. Okay. And this is actually the DC drive example. Okay, so if you have an AC source, so what we need to do is actually we are using uncontrolled rectifier here. So and then we have capacitor. So this capacitor we usually we actually also call as a DC link. Okay, DC link. So this is actually to make sure that the voltage input for the DC-DC converter is a pure DC voltage. And based on the equation for the 3-phase rectifier, you can actually calculate your VDC, which is 3 multiplied V maximum line to line over pi. So this is actually for the uncontrolled rectifier. And then by using DC-DC converter, single quadrant, 2 quadrant, or 4 quadrant, actually the relationship between VA here. So this is actually VA. V armature is actually a buck converter. So the VD. Okay. So by controlling the duty cycle here, we can actually have a variable V armature to control the speed. Okay. So this is actually a circuit this is actually a DC-DC converter. Sorry, this is actually a DC-DC converter for single quadrant operation. Okay, and then as you can see, this is actually a 3-phase rectifier. Okay, and then we have a DC link. So this one is actually your V armature. Sorry, this one is your VDC, and this is actually your V armature. So this is actually the circuit, and as we have known that this is the equation for the V armature. Okay, so this is the example. So we will continue on the next lesson, on the next slide. Okay, next video for this